So students are coming in one.
Well, that's great. I see Assad over there. How are you doing, Assad?
Fine. What about you, sir?
Well, I am sorry for the little glitch, you are halfway around the world. If the P's and the Q's are on the right position, we have problem, right? But
Yes, sir.
that's part of the folklore of living, okay? If there is no problem, if there is no challenge on this life, there is no reason for us to be here. But you still have some time, so,
So we have 1 hour, 1.5 hour.
yeah, so, we hang around, we do something, no problem. Okay, so how was the lecture last time? Did you guys understand properly or what? Hello, is anybody want to talk? No.
Yes, sir.
I got properly the last time. The metric space and the norm spaces. Lecture was good last time.
Oh, cool. Thank you. So while we wait for people to come in, what's the crucial difference between normed spaces and metric space? Can you tell me in few words that anybody can understand? Anybody
Sir,
can
I
take.
will tell you that metric space can be defined on a distance, can be defined normally at every time, while norm space will be only be defined on vector spaces. There is a condition for norm spaces, just can be defined on vector spaces.
Yeah, that's correct. Let me clean it up a little bit to what you said. In order to have a normed space, you need to have the structure of a vector space. To define a metric space, you don't have to have any structure. I define a metric space with the class, your class, the student, the class. And this is a crucial. Now, another question. Can a normed space be a metric space?
Yes, every norm space is metric space.
So if you have a normed space is a metric space, how you define the metric?
So there are a metric space induced by norm.
The metric being induced by the norm, that's correct. So, if you have dx and y should be norm of x minus y. Now, can a metric space be a normed space? If the answer is yes, how? And explain. If the answer is no, tell them why no. Is everybody understood? Can a metric space be a normed space?
The metric space can only be norm space if the metric space is satisfy the condition of vector spaces.
Yes, there is a structure, and what else? Suppose that you said the metric space have to have a structure of vector space. Is that enough? Because you are given a metric space, which they have a structure of vector space. Can
Also,
that be a normed space?
Also, they follow the fourth property of the norm spaces.
Well, that's the property. You just said. Someone said, if I have a metric space, if this metric space is a vector space, then I can have a normed space. Is that correct, what I hold?
Yes, sir.
Okay, now you are missing two things. You need a condition on the metric too. Besides being a vector space, you need a condition on the metric too. Okay, if you don't have the condition on the metric, that cannot be a vector space. I mean, cannot be a vector space. So the norm will be crucial. For example, if you take the norm, let me put on the real line, pick the norm at the metric dx and y is equal to norm of x minus y divided by 1 plus norm x minus y. This cannot be a vector space. This cannot be a normed space. This symmetric will not induce a norm. So we need some conditions on the norm, on the metric, in order to be a vector space. Okay? So the answer is this. The answer is this, which someone answered. Given a metric space, if the metric space has a structure of vector space, and in addition, the metric satisfies two conditions, two extra conditions, then a metric space can be a normed space. Okay, you see the example on the notes that I have to you. Okay. Okay, can we get started or should we wait a little bit more? Well, nobody talks?
What are the two conditions after the following the condition of vector spaces? What are the other two conditions?
You have two conditions. Let me give it to you. Let me see if I have on the book over here. One condition is the let me get exact the condition, okay? More or less I have the condition, but I have to look carefully the condition. Hold on. Here is the condition. The x plus a, y plus a. See, this is a metric space. Okay? And m
Excuse me, sir. Please use to black marker.
Yeah, can't you see no? Can't you see it?
Sir, it is not very clear.
Okay, let me, I have a lot of lights over here. Let me see if, can you see with this over here? Can you see it?
Yes, sir.
Yes, sir.
Okay, so this is a metric space. Okay, in addition, it is vector space. Okay, now in order to this be a norm, I need two more conditions. Okay, I'm telling what the condition is dx plus a, y plus a is dx and y. Okay, this for all x and y in M. Okay, and the second condition is d of ax 0, okay, is norm a, I mean length of a, because this is a real vector space. That's the length, right? dx and 0. If you do this, let me write with this over here. Can anybody see over here? then X in M, the norm is going to be defined as dx0. That's the norm. Okay? Now, I challenge you to show this, to show have a metric space, which is a vector space. If this condition is satisfied, a norm can be induced by the metric, by this over here. Norm of x in M is the distance x to 0. Did you get it? Now, look, for example, pick the real numbers. Is everybody can see there? Hello?
No, sir.
Sir, it's not so clear.
Okay, let me use the blue one.
Internet problem.
Can you see now?
Yes, sir.
That's the real number, and that's a D metric. And x and y being x minus y over 1 plus x minus y. This is a metric. Okay? But this condition over here is not satisfied, so this over here do not induce a norm on R. Did you get it? Is everybody following me? Now, I challenge you as a homework to show if this is a metric space, this is a vector space, this translation over here, see that the translation satisfies. A is a real number, right? Because this is a real vector space, and A is a real number, satisfy this condition. Then this is a norm on D. So I challenge you to show that. Okay? Any question? Does anybody have any question? Come on, guys.
With which
Go ahead.
distance? With
Huh?
which distance? Sir, we have to show that this is the norm, but distance we have to define with which distance?
The distance, that's the distance, right? Satisfy those three properties. So the distance from x to 0, this is a norm. But you need to do this over here, and you need to do this over here.
Sir, we will use distance function of Euclidean distance, having distance which distance on real number. We can use any distance.
This is any distance. This is any metric space.
Okay.
Now, what you have over here, that this, beside being a metric space, is a vector space. There's two conditions over here, metric space and a vector space, do not imply that a norm can be defined, that the metric, I need this condition, this condition. This is, for example, real number is a vector space. The distance that I am defining is this distance over here. And this over here, if I define is not a norm. Did you get it?
Yes, sir. It doesn't satisfy the first condition.
Thank you. Doesn't satisfy the second condition either, okay? But that's correct. You understand, right? Now,
Yes, sir.
metric spaces and vector spaces are related, in somehow. However, a metric space is you have less condition in metric space because any set can be made a metric space. Okay? Now, let's go on. Does anybody have any question? Go ahead, guys. Come on. Someone talk. Nozar is not there today, so she is the spokesman for the class. But I want someone take a charge to answer my question, okay? Now, I define what was a Banach space. I am going to define what's a complete metric space. Remember, metric space and normed space, they can be related to each other, they can be totally unrelated with each other, okay? It's depend. But in a metric space, there is no structure. Now, let me define a couple of things in here. One is this, X, that's normed space. 2, I have MD, a metric space. Think that you always should know. A normed space is always a metric space. Always. Always. Okay? A normed space is always a metric space. But a metric space not always. Now, let's be defined over here. This is important. Is a Cauchy sequence in X is this. You have a x1, x2, xn in X. Okay? Now say this is Cauchy if the limit as n and m is tending to infinity, xn minus xm in X goes to 0. That's the Cauchy sequence. Okay?
Yes,
Go
sir.
ahead. Go ahead, please. Is that everybody can see it?
Yes, sir,
Yes,
we can
sir.
see.
Okay. So that's the definition of Cauchy sequence. Remember, convergent sequence. Okay? I tell that this sequence xn converges to X, again, if you limit xn minus x as n tending to infinity is 0, there is a connection. There is a connection between this guy in here and this guy in here, right? Can you tell me what the connection is?
So it is completeness of completeness of non-space.
No. I am not talking incompleteness. I am just, what's the relationship between these two over there? What's the relationship between those two? Anybody
Well,
can,
every convergent sequence can be Cauchy, but Cauchy sequence is not convergent.
excellent. Hold on a little bit, okay?
Yes.
Excellent. You said any convergent sequence is a Cauchy sequence. And that's the key point to have the next definition. If the sequence converges, the sequence is a Cauchy sequence. But if is a Cauchy sequence, not necessarily it will be a convergent sequence. The Cauchy sequence deal with the distance between two members of the sequences. Doesn't involve x in here. Now comes the definition. If every Cauchy sequence is convergent, then what you say that is a complete normed space is called Banach space. So that's the definition. Okay, the definition goes like this. A Banach space means every Cauchy sequence is convergent. Okay, and that is a expression for the norm. Now, this definition can be applied to metric space, which I will try to define in here. Is anybody can see it?
Yes, sir.
Hello? Okay. So,
Yes, sir.
Xn converges to X in M if limit as n tends to infinity, the distance xn to x is 0. That's the definition of convergence sequence in D. Okay? Now, xn is a Cauchy sequence in M, the same definition. If limit of the distance of xn and xm as n and m tends to infinity is 0. Okay? Remember, what's important in here is in the metric space there is no much structure, but still you can have this. Okay? Now, if comes the definition. If every Cauchy sequence in MD is convergent, then MD is said to be complete. Okay? And this definition, it is extremely important to the structure of metric spaces. Okay? Any
Please
Cauchy
repeat it.
sequences in MD that's convergent is complete. Not every metric space is a complete metric space. Okay? Everything is going to be depend on the norm. Not every normed space is a Banach space, is complete. You need a very special condition to the norm in order to be complete. Is everybody follow me? Does anybody have any question?
No, sir. No question.
Okay? Now, I am going to give a homework. Go ahead. Usman. Usama, right? Usama. Okay, go ahead,
Yes,
Usama.
sir. Sir, repeat it. I can't understand that.
Okay, what I said was any Cauchy sequence in a normed space that's convergent, it's make that a Banach space. That make it complete. What is a Banach space? Is a complete normed space. What is a complete normed space? Every Cauchy sequence on that normed space is convergent. Okay? Now, what is a complete metric space? Every Cauchy sequence on that metric space is convergent. Okay? Now, not every normed space is complete. Everything depends on the norm. Not every metric space is complete is depending on the distance. Okay? Before I
Yes, sir.
give some example and some challenge for you here, okay? Because the theory of functional analysis is based on that, on Banach space. There is one more structure that we're going to put on that called a inner product, which make that a Hilbert space. Okay? Does anybody have any question?
No,
Come on,
sir.
guys.
No, Professor.
I want you to participate, guys. There is no question that's too difficult, it's too easy. If it's too difficult and I do not know it and I try to learn it and I give the answer next time. If I know, I will answer. Now, let me give a example, a homework for you. Homework. Let MD be the discrete let me put so, be a metric space. Where dx and y is 0 if x is equal to y and 1 if x is different from y. Okay? Question. Is MD a complete metric space? Does everybody understand? Does everybody understand the question?
Yes, sir.
Let's go. Okay, so Anna, you're going to be my spokesman, okay? Spokeswoman, okay?
Yes,
Okay.
sir.
So if I ask nobody else over there, but it seems to me the men do not like to talk over there, right? Okay, but please be free to talk and ask any question. The only way that you're going to learn mathematics is if you understand the concept. If you ask questions, take some doubt questions that sometimes you have. I have a discrete metric space. Okay, that's a discrete. Any metric with this over here, that's called discrete. Is the discrete metric space a complete metric space? That means any Cauchy sequence is convergent. Is that true or is false? So I let you think about it. Okay? Any question?
Okay, sir.
So if you take the constant sequence,
Go ahead.
if you take a constant sequence, it is a Cauchy sequence, and also, it is also converges to 0.
Say again. I could not understand. Seems to me there's some echo in you.
If you take a constant sequence like 0, 0, 0, 0, 0, so this sequence will be convergent. It's Cauchy sequence and convergent.
But the point is you have to start with a Cauchy sequence. You cannot start with a Cauchy sequence, a constant sequence, a 0, 0, 0, 0, or whatever. You have to start with a Cauchy sequence. So the key point is let Xn be a Cauchy sequence on that space. Then you're going to show either that's convergent or is not convergent. Will depend on the norm. Did you get it? Is that Assad? You have to start. The key point is you want to try to show this, right? Let Xn be a Cauchy sequence in MD. What that means? That means that dxm xm goes to 0 as m and n goes to infinity. That is your hypothesis. Now, this sequence may be convergent, maybe be divergent. I don't know. That's my question I put to you. Think about it a little bit,
If that,
okay?
that if set belongs to R,
No, this is any metric space. You can think this is the real number, that doesn't matter, but have to be this metric over there. Okay? Did I answer your question?
yes, sir. Sir, then we put a limit on that to converge that.
Yeah, that's what you have. This goes to 0, right? That means the limit as x goes to 0, as n and m goes to infinity. That's what you have. That's your hypothesis. Now, with this metric, you're going to decide whether this is convergent, then you have to exhibit the limit. Or if it's divergent, you tell why it's divergent. Did you get it?
Yes, sir. We put contradiction
sir.
and then we can.
I don't know how you're going to do it, and you can use some contradiction. In order to do some contradiction, you have to assume that it's convergent. If it's convergent, you exhibit a limit, then you can do by contradiction. I don't know what way that you think about it, but you can do by contradiction. Any question? Did I answer your question, Assad?
Yes, sir.
Assad,
Yes, sir.
did I answer your question?
Yes, sir. Yes, sir.
Okay, now remember, what is important over here, the completeness of the spaces is depending on the norm. The completeness of the metric depending on the metric space, depending on the metric. So it's crucial. So before I move on, I'll give this example, which is my book, in the notes that I sent to you, okay? That's normal one. That's the continuous. Is everybody can see it? Is anybody can see it?
Yes, sir.
That's the continuous function 0, 1. That's continuous function. But this norm over here is what you call L1 norm. This is a norm. And this infinity norm over here is the slope of fx. Okay? Two beautiful norms. Now, 2, 1, let me put bigger, is not complete. 2 is complete. See it? It depends on the norm, heavily on the norm. So the is a crucial on that, okay? You have the details of this on my notes books in there, okay? I can go over a little bit that over there. Does anybody have any question?
No,
Yeah.
sir.
Okay. So we also can show that by the subset of if X is a complete metric space, if there is a subset S and it is closed, then subset S will be also complete.
Yeah, the whole point is this fact. Suppose you have MD or a norm space. Okay? Now, if you are on MD, you pick a S subset of N. It's a subset of n. Induce this subset with this norm in here. Okay? Then the question is this. When this is a complete metric space, suppose this is a complete metric space, and when a subset is a metric space. So the question is, S is a complete if and if S is closed in M. This is a very important result. The same holds for this over here, right? So you have a space, a set, in a metric, then a subset. Now you induce this subset as a metric with the same metric over here. Then the question, when this is complete, if this is complete, this over here is complete now, right? S is complete if S is closed, and MD is a complete metric space. Is that what you mentioned?
Yes, sir.
Okay.
If you find some space, like if we find some question like prove that it is a complete or not, we have to find first of all its superset, and we have to show that its superset is complete. Superspace is complete, and then we have to show that this this set is also closed.
Yeah. That's very simple. But the point is, you want to show this is a complete. Okay, you have to pick a Cauchy sequence in this S over there. Okay, you pick a Cauchy sequence in here. You want to show this is a convergent sequence. Because if you take a Cauchy sequence in here, this is going to be a Cauchy sequence in here. So there is a limit in here because it's complete. Okay? So the sequence is convergent in M. So that point have to be in S because S is closed. S is closed if it contains the limit of all the convergent sequence.
Yes, sir.
Okay?
Yes, sir.
Okay. Okay. Let's move on. Now, please try to look this on the notes. Okay. This is not a complete, and this. You want to show this is a not complete, you have to exhibit a Cauchy sequence that's not convergent. And this over here, you have to show that given a Cauchy sequence in here, then have two converges. Okay?
Okay, sir.
Any question?
No, sir.
Now, some facts are with the usual norm. That's the usual metric. Let me put over here. Rn.
Please change the mark.
Or you can see it. You have R with the absolute value. That's complete. Pick Rn with any norm. Any norm is complete. And that's interesting. Okay? Any norm that's complete. In order to show this is complete, you have to use this is complete metric space. Okay? These are complete. So they are in with any norm whatsoever. It doesn't matter. It's a complete metric space. Any finite dimensional vector space is a complete metric space. Is irrelevant the norm. Does everybody understand that? Does everybody can see that?
Sir, kindly repeat them.
Pick Rn with any norm. Remember, last time I put a lot of norms in there, right? Okay.
Yes, sir. Yes, sir.
N norm. N of norm. That is a complete normed space, is a complete metric space. Whatever you want to, with N norm. Complete. In addition, if you look, for example, in finite dimensional space, infinite vector space, for example, not necessarily Rn, but finite dimension, because this is a finite dimensional vector space for those who have taken some linear algebra. And finite dimension space is a complete metric space.
Okay, sir.
Okay?
Yes, sir.
And the reason is because of this. The point is, any finite dimensional vector space is equivalent to Rn. That means, basically, if you want to study any finite dimension vector space, all you have to study is Rn, because they are equivalents. Okay? Any question? Any comments? Come on, guys.
Sir, we can prove that Rm is a complete by the first one, by
Yeah,
using the first one.
this one. Yep. You have. Do you know how to do it?
Yes, sir.
Okay. This we have. This over here is more interesting to do it. Okay? This is interesting to do it because you have to use Bose-Weierstrass theorem to prove this over here. That's complete metric space with this norm there. Okay? Okay, now we have a, before I get into matrix, how much time I have left? 30 minutes, right?
25 minutes.
Yeah, we just waste 1 hour and a half. Okay, but anyway, but the whole point is I am going to give a definition. You can go as a theorem or definition, but let them put as a theorem. It depends how you do. You can use as a definition, okay? You have X on normed space. Okay? Is anybody from you guys teach calculus? Is anybody teach calculus? Calculus 1 or calculus 2? Come on, guys. Talk to me.
Yes, sir.
Did you teach calculus?
Yes, sir. Calculus 1.
Okay.
I've teached it.
Now, there is a theorem in calculus 1, which the theorem is the following. Let's see if I remember. Any absolutely convergent sequence, any absolutely convergent series is convergent. Do you remember this theorem in calculus? Calculus book.
Yes, sir.
Any absolutely convergent series is convergent. I am going to put on the board for you guys here, okay? Say, from calculus, let me put in blue. That's from calculus. any absolutely convergent series is convergent. If you pick any calculus book, you have this theorem. What that says, it says, if absolutely is convergent, if this is convergent, then, oops, can you see here? Xn is convergent. That's a calculus books, right? Can anybody see here? If this is convergent and this is convergent, see? There is no absolute value there. Okay?
Yes, sir.
And this is a calculus book. We have a generalization. Remember on my first lecture, I mentioned that the real number is the key point for generalization of analysis. We're going to have a similar result in here. This is a very nice theorem. I can show to you in a minute. But the point is, this is a result from calculus, which says any absolutely convergent series is convergent. Okay? Now, here comes the X. X is a Banach space if any absolutely convergent series is convergent. Can anybody see that? The same as the
Yes, sir.
calculus in here. Okay? The same. What that means over here? If Xn in X is convergent, then well, you know this is uniform feeling. This over here is convergent. See it? Basically, what this says is this. Is finite if and if is finite. You see what the difference in here is? The norm is outside, the norm inside. And that is the from calculus book. Does anybody know how to prove it? This over here is not very easy to prove, okay? It's on my notes over there. This is not very easy. But this is okay? Does anybody know how to prove this? Come on, guys. Where is Anna? Where is
No, sir.
Assad? Huh? Do
No,
you know how to prove that?
no, sir, I don't know.
It's very simple. I am going to, because this is the thing that I'm going to do. See, the whole point is, there is a generalization. This over here is for the real number, right? There is a generalization for. For example, there is a vector space. It will bear my name. If you look on the books, I define a vector space they call de Souza space. Okay? If you want to prove that de Souza space is a complete, is a Banach space, you have to use that. Okay? But let me very brief do this over here. Okay? Does anybody have any question?
So you have written two conditions on last board.
Okay. Go ahead.
So you can sorry, on the last board, sir, on the previous side of the board.
Okay.
There are two things. One is if summation of norm xn is convergent, then summation of xn is convergent. But below that there is a norm on xn and also norm on the whole summation. So how it resembles the
No,
first
no,
one?
the norm here is inside. The norm is over here is outside. What I'm saying, this language over here, I am translate for this language over here.
So how it resembles the first line? Because the first one, for example, and this one is similar to the right below this, right below. Because norm is inside here and also norm is inside the right below there. And this
The
one
norm is
resembles.
outside. The norm is over here is outside. Right?
Yes,
The
sir.
norm
But
here is inside.
sir, in first line you have written norm inside in first line.
Yeah, this over here said convergent, but convergent in X. That means this over here, okay? When I put convergent in X, because this is a vector in X, Xn is in X. So if I put this over here, and I put this over here, said convergent in X means this over here,
Okay, sir.
okay? Now, maybe you understand when I do this over here, okay? Okay? Now, assume is convergent. I want to show that this is convergent. That's what I want to show. In other words, that is, there is a x on the real number such that xn is x. Or, if you prefer, xn, n from 0 to k, limit of k goes to infinity, this is x. You see, this condition over here, this condition, but this condition would be norm in here, see? See? Or just real number, this over here. Okay?
Okay, sir.
Now, the idea is this. Let Sn be k from 0 to n. Okay? This is a sequence, right? This is a finite number. This is a sequence of number. x1, s2, s3, xn, right? Did you get it?
Yes, sir.
Yes, sir.
Okay? Now, I am going to show that this Sn is Cauchy. This is a number in R, right? This are all in R. I'm going to show this is a Cauchy sequence. What do I have to show? I have to show that Sn minus Sm converges to 0. Okay? Now, what's this over here? Now, I have to assume n bigger than m Or if M is bigger than M, then I switch. Now, what this over here? This is going to be S1 plus S2 plus S3 plus Sn. Let's put over here. S1 plus X2 plus Sn minus this over here. What this over here is going to be? This is going to be S1 plus X2 plus Sn, right? Now, since M is bigger than M, this over here would be what? S M plus 1 plus Sn plus 2 plus Sn, right? Because all this is going to be cancelled.
Yes, sir.
So, in other words,
Yes.
this over here is going to be summation of K from
So n
M
plus 1
to
to n.
N xk. See it? Because the first one is going to be cancelled, right? For example, suppose I have S1 plus S2 plus S3 plus S4. Then I have S1 plus X2 plus X3. Okay? So who's left? Right? Now suppose I have this over here. Who is left?
S4.
S3 and X4, right? And that's what you have in from M. You get it? Okay. So basically, let me go back in here. Then I have Sn minus Sm is equal to Sk, K from M, should be N plus 1, but that's okay. Now I take absolute value in here, right? Now I use the triangle inequality. You remember the triangle inequality? This is Sn, Sk, right?
Yes, sir.
K from M to N. What this over here is? What this, if N and M goes to infinity, what this goes? What this goes? What this over here is? What the hypothesis is? The
Zero.
hypothesis,
Absolutely convergent.
is this. Is convergent, right? That's the hypothesis. An absolute convergent series, right? So this is convergence, and this is the tail of the series, right? So that means this goes to 0. Okay? Because of this, right? So
Yes,
I
sir.
use that absolutely convergent. Because of this absolute convergent, then this goes to 0. That's the tail of the series. Okay? So what that means? Sn is a Cauchy sequence in R, right? Can anybody finish from there? Can anybody finish from there?
Since R is complete, so Sn will be convergent.
There we go. So that means, look what Sn is. Sn is, what I pick, X, right? Xn, that's what this is, right? So that's convergent. Okay?
Yes, sir.
So I still have 9 minutes. So now, to prove in general, the reason I mentioned this over here is the fact that we are using things that we know very well. Okay? However, when you say a Banach space is a Banach space if every absolutely convergent series is convergent, that's come from the real number. Okay? Now, there is another observation over here, which you don't see this in any book whatsoever. I'm going to mention to you right now before I move to my last 5 minutes, is this. You have the definition of norm. 1, 2, 3. X plus y is less. Okay? That's making normed space, right? If this is a norm. Okay? Now the question is this. Since this over here is finite, if I have x1 plus x2 plus xn, this is. Does everybody follow me?
Yes, sir.
If it's true for 2, you
Yes,
can do
Prof.
this by induction.
Yes,
So
Prof.
now, is that Miss Nozara came in? Welcome to the world, Miss Nozara.
Yes, Prof. Thank you very much,
Okay,
Prof.
so the
Very
question
nice to
is
meet
this. Nice to talk to you. So I have a replacement for the spokesman. Anna was the spokesman because we were not there early. But anyway, the question is, is it true for infinity? In other words, is that true? You understand, right? What I did, right? If it's finite, okay, you can use induction and you prove this. Now the question is that true if I keep on going, if that's infinity, right? And from the, is that true? Come on, guys. Everybody's so quiet over there. Is that
Prof,
true or false?
It is
Go ahead,
blur on my
Nozara.
side.
Okay. Is that true or false?
Sir, is it summation from 0 to infinity? Sir, it is not very clear.
This is infinity, right? See, this over here, let me write this. What this over here is? This is xi, I from 1 to n. This is summation from xi, oops, I'm sorry. I from 1 to n. You see it? This is finite. For finite, that's true. Now the question is, if I replace this by infinity, is that still true? You understand or no? Remember, when you do mathematics, you maybe not understand how to solve the problem, but you should understand how the problem is. You may never solve the problem, but you have to understand the problem. This is for finite numbers, really? 2 numbers. From this, you can have a finite number, x1, xn, then it's still true. You can do this by using induction. Okay? My question is this. Can I continue going this over here? See? this is finite, this is finite. Now I have infinity, right? I have x1 plus x2 plus xn, da 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 da. Is that true? That's 1 plus xn plus da da da. See it? Is that true?
Yes, sir.
Is that true? Huh?
Sir, it seems to be true.
Seems to be true. I like when you said seems to be true, but mathematics is not a question of opinion, but I thank you for, try to answer this. It's true. You correct. If the space is a Banach space. You get it? The triangle inequality is true for infinite dimension if the space is a Banach space. You don't see this in many books, okay? You don't
Right,
see.
sir.
It means
Is that
it's
what I
true
understand,
for
right?
only Banach space. It
That's
means
correct.
it's true for only Banach space.
There we go, Missy. Sheikh. Is that Sheikh?
Delaware's Sheikh.
What? Delaware?
Sheikh.
Okay. Delaware. Yeah. This is true. And if the underlying space is a Banach space. Okay? You have too many little details that, we just, for some reason, waste 1 hour and a half over here. I did not get into in what I want. One point is, if you want to understand analysis, if you want to be able to produce some mathematics, one thing that you have to understand perfectly well the concept of norm, the concept of completeness, the concept of Cauchy sequences. What's the difference between a convergent sequence and a Cauchy sequence? A Cauchy sequence, there is no limit involved over there. If the space is complete, you can't show that the sequence is convergent but not exhibit the limit. So those little things are very important if you want to continue in the producing some mathematics. Does everybody understand what I'm talking about?
Yes, sir.
Are the details. There is a saying here in America which says the devil is on the details. Okay? So you have a lot of problems. There's notebooks that I gave to you over there. That is a book that I am writing with a former student, my PhD student, Ed Kwazai. And we have a lot of problems over there. We have even the D'Souza spaces there. You have some spaces over there that you don't see usually, and this is going to be published soon. So I just make these notes over there for you on this. But I did not get what I want to get was linear transformation. Okay, I don't know if Ali wants me to give another lecture over there. I was suspecting that we might have a problem with the connection. That's the only country that I have been lectured that we have some problem with the connection over there. I don't know what indeed is for security or for whatever reason is, right? But at least, if I am allowed, I not mind to give another at least 1 hour more now to go on linear transformation, Banach spaces, Hilbert spaces, complete metric spaces. Linear transformation is the heart of functional analysis. The reason that you study linear transformation because there is a lot of concrete problems, integral equation, integral transformations that are very important, and it is sitting on Banach spaces. So it's very important for people to understand the concept. Okay? Okay, I don't want to spend any more time because I am 1 minute over my time. And probably if I go 2 minutes, Miss Arnaud is going to tell, hey, Dr. D'Souza, you are 2 minutes beyond the time. But
No, sir.
anybody, I know that's late over there. Over here is early, right? But anyway, if anybody have any question, if I am allowed to, give this hour and a half so I can go on linear transformation. I don't know if you want to do that, I don't know if you maybe get tired of my lecture, my Brazilian accent, right? Okay? Does anybody have any question? Does anybody have any suggestion? Anybody have any comments?
Hello, Prof.
Yeah? Go
So
ahead,
you can
Professor
take
Ali.
you can take another 10 to 15 minutes.
Okay, wow. So you are the boss, right? So he said you can take. Okay, so I'll take it. So I can mention so one reason that you study Banach space is look for linear transformations or linear operator. This allows you to study more complex situation like partial differential equation, ordinary differential equation. Okay? So what's a linear transformation? Then you have a t from x. Now you need to have this structure in here. Okay? Normed space. Then you have another normed space. You send a x in tx. You say that a t is linear if 1 t x plus y is tx plus ty. 2 t alpha x is alpha of tx. Okay? Now, linear transformations are very important in analysis because a lot of operators are linear transformations, right? And for example, let me give an example in here. The derivative, take that, the derivative, that means t of f, the derivative of a function. That's a linear transformation. Take a f integral from 0 to 1 ft dt. That's a linear transformation. Okay? That's a linear transformation. Now, we have t is bounded linear transformation if tx on the normal y is a constant normal y, normal x in x. That's called t is bounded linear transformation. So the whole functional analysis is to characterize those linear transformations that are bounded. It looks very simple, okay? It's characterize all the linear transformation that are bounded. Example, let's say t from a continuous function on 0, 1 into the real number, which send f in T of f integral 0, 1 ft dt. Okay? Now, I have to tell what norm I'm going to put in here, right? See over here? I have a norm, and also I have a norm in there, right? So, this over here, to be explicitly, I am going to put, all right? Then I put the infinity norm in here. Now, this over here is the real number and the absolute value. See it? Now, I want to show this is bounded. So, what I do is this. Now, I am in here. So, I take absolute value in here, right? This is a number. From property of integral, this is less than 0 to 1 ft dt, right? This property of the integral, you can put it inside in here, right? Now, this over here, ft, is less than the sup of fx, x between 0 and 1, right? And this is norm infinity. So this over here should be less or equal integral 0 to 1 norm infinity t. So this is a constant. I can pull it up from the integral. So on this side I have tf. On this side I have. So what I have left is this. What integral this is? 1, right? If you integrate, this is t between 0 and 1. So therefore, tf, see? So this is a bounded linear transformations. Okay, so the study of functional analysis, in a sense, begins over here. Because then you have the closed graph theorem. What the closed graph theorem is a mechanism, is a theorem to determine when a function is bounded. Over there. Function is bounded. What the open map theorem is exactly the same. What the Hambanac theorem? The Hambanac theorem is a very powerful theorem. Okay, now this over here, I am in a normed space into a normed space. If I now take a normed space into a real and this is called linear functional. Linear functional. Okay? And the set of all the linear functional is called the dual space. One of the biggest problems that you have in analysis is to determine the dual space of given a bounded linear functionals. Okay, that's called Riesz representation theorem, and these are connected with Hambanac theorem. So now is where functional analysis gets started, because what I mentioned, vector space, normed space, Banach space, okay, is going to be used to study linear functionals. There is an area of mathematics that is being studied very deeply, and some people on UMT study is sort of nonlinear analysis or the fixed point theorem in metric space. Okay, it's situations more complicated if the transformation not linear. Linear satisfy this condition over here. You have some transformation. Remember, we call transformation, but that's a function, right? It's a function from this space over here, from this space. This space have a structure of normal space. This have a structure of normal space. We call linear transformation or operator because you just deal with more complex spaces, okay? So now we have the structure of functional analysis. So the next one, so there is a lot of theorems over here, okay? Since I don't have any more time, okay? One very important is this over here is duality. The duality is important, okay? That's if you had the opportunity, they call Riesz representation theorem. What is the set of the dual? That means all the bounded linear functions. You want to characterize all the bounded linear functionals. Okay, and this in general is a very complicated problem. However, they are naming called Riesz representation theorem. Okay, it's a beautiful one. I can mention this sometime, but anyway, my time is almost up over here. I have 2 minutes. Is anybody have any questions? Is anybody? For example, all the linear transformation. If you have a linear transformation from Rn, put Rn over here, in Rn, at the matrix, and this is beautiful. Any linear transformation from Rn to Rn is a matrix. If you have a linear transformation, T, let's see, from R2 into R2, this T is a matrix, A, B, C, and D. See it? So since we don't have much time, then, that's it. Does anybody have any question? Anybody have any suggestion, comments?
Sir, we have translation, rotation. These are the linear transformations.
Well, some you said the translation, when you look the linear transformation, you just have to look to these conditions over here, right?
Yes, sir.
So if you have the translation, let's put on the real number, right? You want Tx be T of x minus A. So you basically have to do and say that, to satisfy this condition, let's put Tx is equal to x minus A. Is that a linear? No, it doesn't satisfy this condition over here, right? See it? This is different from, see it? Now, the rotation is different. The translation, see, I'm just put this over here, right? So this is not linear. Remember, to check if they find linear, that's all you have to do, right? If satisfy these conditions linear, if it doesn't satisfy, that's not linear. Okay? Now, remember, this over here, if you look, all the linear transformation from R into R, pick a linear transformation T from R into R. This have to be the lines through the origin. See? The linear transformation will be this type over here. See? Now, if you translate this, That's not linear. When I'm not linear, look over here. If I put 0 in here, alpha is equal to 0. I have 0. I have 0. So T0 have to be 0. If a linear transformation have to be 0. If you look this over here, T0 is minus A. So this is not linear. See it? So all the linear transformation from R into R are lying through the origin. Now, if you want the linear transformations from R2, we're going to finish over here, okay? From R2, it'll be planes. All the linear transformation, it would be this, AX plus BY, CX plus DY. That means you'd be planes through the origin. They have to be T0, 0 have to be 0. Otherwise, it's not linear. I don't want to get your time off, okay? And that's it.
Thank you,
Any
sir.
question? If anybody want to talk and ask question, I am here, so I am not going anywhere right now. Does anybody have any question?
No, Professor.
So, Delaway, are you a PhD student or master student?
Professor, I'm a master student.
Okay. So what you going to do your master on? Analysis, algebra, or what?
And no, it's my coursework.
You don't know yet, right?
Yeah, no, I don't know yet.
Yeah, no. You know, Analysis Beautiful, Lee is doing a good job over there. So, you know, on metric space, that's what he works on.
Professor,
ahead.
my interest is on analysis. Actually, inshallah, I will. My research will be in analysis.
Yeah, analysis. Yeah, I am suspicious to talk analysis. I am a harmonic analyst. It's complex analysis, measure theory, functional analysis, harmonic analysis. That's my area. If you look
Okay,
in this notice over there, there is a D'Souza spaces over there. You can see.
Yeah. I read your notes.
So you know, it to me is one of the beautiful area, and you can apply in partial difference equation. You can apply in statistics. You can apply in anything. If you want to do anything in area like PDEs,
Yeah, PDs.
that's complicated stuff. If you want doing dynamic system, you need to have some analysis. If you want doing a numerical analysis, you have to have some analysis. So, you know, analysis to me is the heart of the whole mathematics.
Yeah, it's the heart of all mathematics.
Well
You are
said.
true.
Go ahead. What's Assad was talking?
Yes, sir.
You have any question?
No, sir. Thank you, sir.
Hey, look, I enjoy very much. You know, I could not finish to do this stuff. Maybe after few weeks, if Professor Ali invite me again, I don't want to talk about linear functional, part of functional analysis. But otherwise, you know, you have my email over there if you need any have any question and comments, be free to contact me, okay? I am available, okay?
Okay, sir. Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you so much, Professor. I really enjoyed your classes.
Yes, I enjoy. I would like to talk a little bit more, but you know, but I enjoy very much. It was a great pleasure to me, honor to be able to spend some time with you and doing some this functional analysis over there, right? You know, except for the glitch on internet, you know, everything else.